Hello, am I audible to all the participants?
Yes, sir.
Yes, sir.
Okay, sir. Good morning, dear participants. We are going to begin session 1 of day 4. The expert of this session is Professor Pratik A. Barot, sir. He is a professor in Computer Engineering Department of Government Engineering College, Gandhinagar. He is pursuing his PhD in the area of machine learning and having 15 plus year of teaching experience. So we are having good opportunity to begin our first session with such a eminent personality. We will learn concept of data difficulties from sir. So without wasting precious moment, I am handing over to the expert of the session, Professor Pratik A. Barot, sir. Please, sir.
Thank you very much, Ghanshyam sir, for introducing me with nice word. Good morning, participants and Ghanshyam sir and team FDB. So today, let me save my slide first of all. So today I am going to present the session on the data difficulties. Now, when you study about the machine learning and you don't know about the data difficulty that you have to address, then it creates lots of problems. So in today's session, I try to address some of the data difficulties which are important to know, important to understand before you start your journey as a machine learning expert. So I hope my slide is visible and I hope that I'm audible to everybody. So let me start this session. So this is the outline of today's session. We will see how the data difficulty, what is the data difficulties are and how its impact on the machine learning algorithm. We will discuss about the multivariate attribute distributions that used to identify the relationship between the dependent and independent variables. Then we address some of the data difficulties like the small disjunctions, class overlapping, and we will try to see those, visualize that class overlapping with 2D and 3D graphs. And then we will see how these difficulties adversely affect the classifier performance. We will also evaluate some of the performance measures. So that is the evaluation of evaluation measures. And then in the last I will explain what can be the remedies of the unbalanced data. So let's start this journey. And so as a machine learning expert, if you have a good quality data, then your half work done in machine learning. So suppose you are a machine learning expert in some company and you have a good quality data, and you are sure that every day you have a good quality data to implement the machine learning algorithm, then your half work will be done. What you have to do is you have to just apply the machine learning algorithm straight away and your work is done. So that makes your task, your job very easy. And your salary would be half too. Why? Because if you have a good quality data and if you are sure that every day you have a good quality of data as a machine learning expert, then no need to pay a good salary to the machine learning expert, because the data quality is one of the important aspects that we need to check, that we need to analyze before we jump into the machine learning algorithm. So the machine learning expert, the data scientists are getting the handsome salary because they don't have a good quality of data. So this is something good as machine learning expert. Okay, so this is the you can say the objective, that the first question that comes in the mind, that when you do some experiment with the machine learning algorithm, the question may rise in your mind that why machine learning algorithm shows different performance for different data set. Why we have a different performance for the different data set? So we know that yes, we have a different performance for different data set, but we don't know the reason. The second question is why different machine learning algorithms show different result for same data sets. This is something that we already experienced, that yes, machine learning algorithm shows the different result for even same data set. We have a different result for SVM, decision tree, neural network. But why? The question is why? That we don't know. The third one and most important one, and that may surprise you, that why it is not appropriate to select the classifier just because it gives 90% of accuracy. Third question may surprise you, that even if the classifier gives you the 90% of accuracy, that doesn't qualify that classifier for the practical implementation for the products and servers. And the last one is the why study of the data characteristics is important and how to do it. We are going to address all these 4 questions and much more. So let's start. The quality data helps in achieving high performance, and bad quality data affects the performance of learning algorithm. So before you decide to apply the machine learning algorithm, study the data set. Try to understand what are the characteristics of the data, what are the difficulties are there in the data set. So let's begin. This is the data difficulties that we face. The first 2 are very common, and I think everybody knows about those difficulties. And those difficulties are missing values and noise. If you have a moderate knowledge of machine learning, you already experience this difficulty, that missing value and the noise. Then the third one is the data unbalance. Fourth one is lots of difficulty like the small disjunctions, strong overlapping among the classes, too many minority examples surrounding by the majority class examples, within class imbalance, borderline examples, and a lot more. So what we did is, for this study, we consider these 6 data sets. Now, as I told you that before jumping into the machine learning, first we need to understand the data set. So that's why the slide is here, the data set information. Because I am going to present this study by considering these 6 data sets. So it is important to know about this data set. The first one is the biopsy cancer data set, where the imbalance ratio is quite okay. That is 1.89. So still it is imbalanced. The new thyroid data set had 3 classes with the imbalance ratio of 4.84. Then the HIV, diabetes, mammography, and so on. Now in this 6 data set, you might notice this. The subtle data set has highest imbalance ratio. Imbalance ratio is what? Imbalance ratio is the ratio of majority class instances divided by minority class instances. In other words, imbalance ratio is the ratio of positive class instances divided by negative class instances. So subtle has highest imbalance ratio of 66.67. Why? Because it has 49 instances of negative class and 3,267 instances of positive class. So this is the largely imbalanced data set. Followed by the mammography, then new thyroid, HIV, then diabetes, and cancer data set. So this is the introduction. Now let's start with the difficulties. The first one, very basic, noise and missing values. Now data set that we have, among those data set, the biopsy cancer data set has some missing value, around 16 missing value for attribute V6. V6 attribute that I actually renamed as V6, but it is named as bad nuclei. So what is the remedies of the missing value? That's simple. Take the attribute mean, replace the missing value with the attribute mean value. You may get rid of the missing value. That is the very general idea. But when you have a data set with huge ratio of misclassification cost, so the question may arise: what is the misclassification cost here? For example, in cancer patient data set, if you misclassify non-cancerous patient as a cancer patient, then it requires more tests, and that require more financial expenses. But if you misclassify some cancerous patient as non-cancer patient, then the misclassification cost is loss of life. Because if your machine learning algorithm misclassify the cancer patients, then that delay the treatment procedure, and the delayed treatment procedure ultimately result into the loss of the life. So that misclassification cost is huge. Now suppose you have this kind of a data set and you want to handle the missing value, and you realize that all the missing value falls into the class which has high misclassification cost. So at that time, instead of taking the attribute mean, you have to take the class specific mean value. The other thing that you can use is you can take the global mean. Now same remedies can be applied for the noisy data. The noise, what is the noise? In the diabetes data set that we use, in diabetes data set, when we analyze, we found that zero blood pressure for some of the patients. Now zero blood pressure is not possible for the living human. That means it's noise, obviously. Zero blood pressure is not possible. So that means it is noise. 1000 marks is not possible. That means it is noise. Minus 45 age is not possible. That means it is noise. To handle the noise, you require some domain knowledge. And if domain knowledge is not available, then again you take the generalized approach. That generalized approach is take the mean value of the attribute. So I'm not okay. So this is what noise and missing value, and this is very basic one. So I'm not taking much time for explaining those things. So let's move to the next thing, that is multivariate attribute distribution. This multivariate attribute distribution is useful to know if your problem is separable for a given attribute or not. Now, why it is important to know if the problem is separable or not? Because if the problem is separable, linearly separable, or it is separable by some attribute value, then that means your SVM work, if you select the SVM, support vector machine, then you will have a better performance. And if you have some attribute which provide the linear separation among the classes, then even your decision tree can use those attribute as a splitting criteria to split the data. In the next slide, we will see the attribute distribution bar. So in the next slide, we have a attribute distribution chart, multivariate attribute distribution chart for all the data set. But if attribute have, before going into that slide, the point that you need to note is if attribute have a distribution bar which are dominated by either positive or negative class. So positive or negative class is what? We are in machine learning algorithm. If we have a supervised learning, then we have a predefined class label in the data sets. And if it is a binary class data set, then we have a two class, that is positive and negative class. So if in attribute distribution bar, if we have some bars which are dominated by positive or negative class, then decision tree family can have capability to use it for the generation of branches. Let's see that. Now this is the statement that we note here, and in coming slide we also test this statement whether our belief is wrong or right or wrong. This is the slide. Now let me zoom it. So this is the multivariate attribute distributions. In this data set, we have a total 9 attribute plus class attribute. So this portion describe the numbers of instances of each class. So this blue bar indicate the number of positive instances, that is 458, and this red bar indicate the negative instances, that is 241. Now, please, the positive and negative are just a name. That doesn't mean that negative class is not important and positive class is important. Even we can call this as a positive and this as a negative. Okay, but usually in textbooks, the majority class is represented as a positive class. That's why we call it here as a positive. So this is the distributions. Now let's see how the attribute distribution is. So here we have a distribution for the V1 attribute. This, the first tiles. Now you can see here that when the V1 value is more than 5.5, we have a bar which are dominated by the negative class. If the value of V1 is less than 5.5, then we have a bars which are dominated by positive class. So this could be the useful thing for the decision tree algorithm and the SVM, support vector machine algorithm. Let's see how the V2's distribution is. Again, V2 have a very good dominance of negative class if the value is more than around 2.5. Even V3 has class distribution. Now that means in this breast cancer data set, there is very good separation among the negative and positive class if we analyze this multivariate attribute distribution. Let's see what happened to the HIV data set. Now here you can see, now first of all, let's see the color coding. So here, this red represent the positive class and blue represent the negative class. Now, if you see here, there is a very less numbers of bar which are dominated by the blue color, that is the negative class. So that means the most number of bar for all the attribute A1, A2, A3, A4, A5, A6, A8, A8, we have 8 attribute, and almost for all the attribute, the majority class has dominance, except for this bar, where the minority class, that negative class, has more number of instances. So this bar and this one, these are the some of the things that we have. So if we compare these two data set, I can say that we will get good performance for breast cancer as compared to the HIV. So let's see the next data set, that is the mammography. And I hope that you remember that mammography and subtle data set are the data set which has highest imbalance ratio. So in these two data set, there are very few negative class instances. Let me zoom this. Okay. Again, the red represent the negative class. Do you able to identify any bar, any attribute bar with the negative dominance? I can't do that. Can you do that? Are you able to see any dominance bar, any bar which is dominated by the negative class? I am not able to see. Let's see the subtle data set, which has the largest imbalance ratio. Again, let's first of all, blue is the negative and red is the positive. So see, is there any bar? Yes, there are some bars. There are some small bars which are dominated by the minority class instances here as well. Okay. Now there are the negative class instances are only 49. So if you sum up this thing, that is 8 plus 6 plus 7 plus 9 plus 3. That means out of 49, almost all the instances are covered with some bars. That means even if the subtle data set has largest imbalance ratio, as compared, it is more separable as compared to the mammography data set. Then these two data set, diabetes, okay. Red represent the negative class. So even in the diabetes data set, we are not able to find any distribution bar which is dominated by, yes, these are some of the bars which are dominated by the negative class instances. Now, how to calculate dominance? Now, so let me give you the example. Now, this is suppose the bar, right, with 136 instances. Now, if you look into this bar, the majority portion of this bar is blue colors, and the small portion is of red colors. That means if the blood pressure value is 61, that means from the total number of instances, if the blood pressure value is of 61, then there are majority instances are belongs to the positive class as compared to the instances which are belongs to the negative class. So this what the bar represent. So okay, so diabetes, for the diabetes we have some sort of distribution bar which are dominated by the negative or minority class. The new thyroid data set has 3 classes. So we have 3 colors, and here we have some dominance. Here we can see some dominance of negative class instances. Now, why I emphasize on negative class instances? Because this data set belongs to the medical domain. In the medical domain, the minority instances are more important than the majority instances. Why? Because if you analyze any hospital data set, then you will find at the end of the year you will have a data set of, say for example, of 10,000 patients. Then it may be possible that out of 10,000, 1,000 patients are diagnosed with the disease, and remaining 9,000 patients are diagnosed without disease. It may be a cancer hospital, it may be a COVID hospital, it may be anything. So this imbalance is the difficulty. And when you have a distribution bar, when you analyze the multivariate distribution bar, and you found that we have a class imbalance present, and we do not have any attribute distribution with the dominance of the minority class, then that means we have a huge problem. That means our classifier algorithm are going to perform suboptimally for this particular data set if these difficulties are present. Now the thing, okay, so let me explain that how we can create this multivariate attribute distribution. For that, you can use the Vika. You can use the other tool as well. So here I already opened the files of the cancer data set. These are the attribute. This is the class value that we already see. And this is the Vika, okay? And then click on the visualize all, and you have a multivariate attribute distribution in front of you. So from this window, you can analyze your data set. You can analyze the distribution of your data set. Now, why it is important to analyze the data set before machine learning algorithm? Because if you are sure that yes, my data set is linearly separable. Yes, I have a data set where the multivariate attribute distribution shows the good separation, then I can go for the decision tree algorithm. If the data set is linearly separable, then I can go with the SVM algorithm. So this study of multivariate attribute distribution helps you in selection of the optimal machine learning algorithm for your problem. So now let me close this. So, okay, so we will, okay, I hope you note down some of the things that from this 6 data set, breast cancer data set had very good distribution, very good separations for the attributes. HIV data set has less separation, but still there is a separation. Mammography data set has worst separation. Subtle data set, even subtle data set, there is some separation. Diabetes, again, bad separation. New thyroid, good separation. Okay. Now, this observation, we will relate this observation at the end of this this presentation when we analyze the performance of the classifier. Now next one is the small disjunction. What is the small disjunction? As per Georgie, the small minority disjunction affect the performance of the classifier. Affect the performance of the classifier, that means it reduces the performance of the classifier. So what is the small disjunction? Small disjunction, that means you have a data set and one of the class instances are scattered around in a small disjunct which are surrounded by the majority class instances. So in that case, you have a data structure, data graph like this. So this is the negative class instances. Okay, and this is the positive class instances. Again, here there are some minority class. Again, you have a positive class instances. Few negative class. So this is what the small disjunction. Now what happened there? When you train your model, your machine learning model on this kind of a data set, your model will misclassify these minority instances. Why? Because your model will give more priority to the positive instances which are in majority number. So that's why the small clusters, if the small subcluster is dominated by minority instances, then it may possible that performance do not have a severe effect. But if such subinterval has less number of minority instances, then they may get misclassified. Some of the algorithm like decision tree, SVM, KNN, K nearest neighbor, they do not show the optimal result in case of minority disjunction. Now to identify whether we have in our data set whether there is a small disjunction, or we need to analyze the data set. So what to do? How to analyze? Now for that, I create one procedure. When I have a data set, when you give me any data set, then my priority is to check whether the small disjunction are there. Now to check that, what I will do is I have to create the clusters. So for this analysis, what I do, I create the 6 cluster for each data set using the K-mean algorithm. Then I merge that cluster information with the original data set information. I merge the cluster information with the original data set information and then plot the graph. So when I plot the graph, I have a complete information about how the clustering and what is whether the clusters are dominated by the minority or majority class instances or what. If there is a dominance of majority class instances or positive class instances, that means there is a higher chance of misclassification of negative class. Now let's see that plot. So A is for breast cancer, B is for HIV, C is for new thyroid, D is for mammography, E is for shuttle, and F is for diabetes. Now again see here. This is the analysis of small disjunction. Let me zoom it. Okay. So there are 6 clusters, right? And I just merge the cluster information with the data set information so that I can represent the numbers of majority instances, minority instances in each cluster with color coding. Now here, okay, here I use the red as the negative class instances and blue for the positive class. So for this data set, the first one is the cancer data set. For this data set, we have some clusters which have a dominance of negative class. Here you can see, here you can see, here you can see, here you can see. So that is the second advantage of the cancer data set that we have. The first one is when we analyze the multivariate attribute distribution, we have a good separation. When we analyze for the small disjunction, again we have a again there is a less disjunction in the cancer data set, because the clusters, all the 6 clusters, out of 6 clusters, the 4 clusters which are the in fact are the small cluster, but they are dominated by the negative instances. So when they have a dominance, it's easy to identify those instances. Then the B is for HIV. Now see here, again we have a difficulties in case of HIV data set. The small disjunction reveal that the clusters, all the 6 clusters have a dominance of positive class. So if you even if you apply the clustering algorithm, there is a high chance of misclassification of negative class. For new thyroid, okay, so see, new thyroid data set has 3 classes, and there is a good, okay, so there is no small disjunction in new thyroid, because we have a one cluster which is dedicated for one class. This cluster is dedicated for another class, and then we have a 1, 2, 3, and 4 cluster which are dedicated for the third class. So each class in new thyroid has its own cluster. The instances are reside in their own clusters. So that means the SVM is going, I'm sure that SVM will perform better in new thyroid and in the cancer data set as compared to the HIV data set. Now let's look into the D. D is what? D is the mammography. Okay, mammography, which has largest imbalance ratio, which has a large imbalance ratio. So can you able to see any clusters with the dominance of negative class? I am not able to see. So that create the problem for the mammography. And that means we are going to have a less performance for the mammography data set. E, that is the subtle data set. Now subtle data set has a highest imbalance ratio. That is one of the data difficulty. But when we see the small disjunction analysis, we found that for all the negative instances, there is a one cluster. So all the negative instances are forming one cluster, one closed cluster. That means it's easy to identify those instances by the classifier algorithm, by the machine learning algorithm. That means the machine learning algorithm will show good performance for the subtle data set, even if the subtle data set has a largest imbalance ratio. So just one data difficulty, we cannot jump into the conclusion that, okay, there is a one data difficulty, we have a less performance. We have to analyze all the data characteristics. The last one is diabetes data set, and in diabetes data set also we have a one dedicated cluster for the negative class. So again, the point that we note here, we have a very good, we have absence of, we found absence of small disjunction in case of cancer, subtle, and then diabetes and new thyroid. Okay. In case of HIV, the disjunction, small disjunction is there. In case of mammography, there is a high volume of disjunction. Okay, so that is what we're finding from this study. So okay, so this is we already discussed about the thing, and then KNN and SVM classifier. do not perform well in case of such disjunction. So if you have a disjunction, in case of mammography, we have a very bad, very worst disjunction is there. So I'm sure that SVM is going to perform worst in case of mammography data set. Okay. Further, from my observation, I found that if you have a subcluster and if it is dominated by negative class instances or minority class instances, that means there is a high similarity between the negative class instances. Now, when you have a high similarity between the class instances, that means your machine learning algorithm will going to perform well. If you have a less similarity between the class instances, that means machine learning algorithm has no idea about how to predict those class instances. Okay. The next one is the class overlapping. Okay, any questions up to this? Actually, I want to cover many things before 11:30, so you may found that I'm going very quickly, but I also want to show some of the practical things as well in this session, especially for the MDS and for the class overlapping, to visualize the class overlapping. Okay. Okay, so let's move to the next thing, next data difficulty or next data characteristics, that is class overlapping. Now, as a machine learning expert, if you found that your data set has a huge class overlapping, that means you have to do something. You cannot apply your machine learning algorithm straight away. If you do that, then you have a less performance. Now, so to visualize the class overlapping, we need to plot the multidimensional data into some graph. It is not possible to do that. When you have a multidimensional data, it is not possible to plot that graph. Then what is the alternative? You need to change the data set, the multi-dimensional data set, into the two-dimensional data or maybe three-dimensional data. Multi-dimensional data, that means the data set which has a large number of attributes. If your data set has a large number of attributes, it is not possible to plot that data into the graph and to visualize whether the class overlapping is there or not. You need to convert that multi-dimensional data into the two-dimensional data. Now the question is how to convert that. For that, I'm going to explain one technique that is called multi-dimensional scaling. In short, MDS. So multi-dimensional scaling can be used to convert multi-dimensional data into the two-dimensional form. And the important thing is it still preserves the intrinsic properties of the data object. So that means it is not just scale down the data set. It also maintains the characteristics of the data set. So that is the advantage of the MDS. So it reduced the number of dimensions, but still it maintains the characteristics and properties of the data. That is important. And some researchers also claim that the MDS plot is used to visualize the data distribution. That's perfectly fine, because the MDS technique keeps the original data distribution while scaling down the dimension. So that is important. If you use like the other dimension reduction, like the principal component analysis or matrix factorizations, then it may possible that the intrinsic characteristic might lose. But in the case of MDS, it maintains the characteristic, the original distribution of the data. So that's why it is important. So multidimensional scaling is used for visual representation of the similarity and dissimilarity between the objects. And for that, now this is the code of MDS. This is the R language code for multidimensional scaling. This is the R language called for multidimensional scaling. Now let me show you this thing in practical in R Studio. Okay, this is the code. I use the cancer data set here. Let me run this. Okay, so let me run this. Okay, now see. I hope my screen is visible. I think I have to share my screen here. Okay, so I am going to share my screen. So wait a minute. Okay. So the R Studio screen is visible now. Is it visible?
Yes, sir, visible, clearly visible.
Okay, okay. So what I did actually, I forget to share the screen and I just run this code. Now let me run it again. Okay, so when I run it, this is the original data set, that is V1, V2, V3 and with 9 attribute, and last one is the class attribute. Now what this code we had done, this code reduced the number of dimension. So we have a 9 dimension plus class, that is 10 dimension. It reduced it into the 2 dimension and I just bring that 2 dimension here. You can see here those dimensions, dimension value actually. So these are the 2 dimensions. The first one is the serial number. Okay, so you can ignore that thing. So these 2 are the dimensions which are created by the MDS. And once we create the MDS, this line plot this 2D data here on the right hand side, right hand corner. So that way we can plot a graph of multi-dimensional cancer data set and we can visualize the distributions. Now from this distribution, from this graph, we are not able to identify whether the class overlapping is there or not. Yes, we can identify whether the data overlapping is there or not. But we want to find out whether the class overlapping is there. So what to do? For that, again what we did, we combine this 2D data with the class variable. Now I hope that this is fine, right? So let me close this R Studio. Now in slide you have a MDS code. And when we do this, we have this output. This is the output. The first one is the coordinate 1 and coordinate 2 represent the new dimensions which are created by the MDS. This figure is for HIV data set. Okay, so this is the distribution of HIV data set. This is the distribution of the cancer data set. Okay, so data overlapping is seen, but what about the class overlapping? We combine the class with that 2D data. When we combine the class with the 2D data, two-dimensional data of MDS, and then we plot this graph. So here, the yellow represents the negative class instances, and the purple point represent the positive class instances. Now, this is for the cancer data set, breast cancer data set. So here, do you think that can we visualize the any class overlapping is there? Do you think the class overlapping is there? The class overlapping is not there. Or maybe I am not sure. The class overlapping may be there underneath this purple point, because this purple point is the dense area. This is the dense area. There are a large number of instances of positive class instances are here. So it might be possible that negative class instances are underneath to this area. So how to visualize that thing? For that, we have a 3D class distribution. We have to visualize the 3D class distribution. So this is the 3D graph. This part indicate positive class instances. This class indicate the negative class instances for the cancer data set. Now let's visualize. I hope. Okay, let me see if I can do that. I can play this video. Okay, there may be some problem in playing this video. Okay, I can do that. Now here the 3D view of all 6 data set is here. So this is the 2D view, right? This is the 2D graph that we already seen for the breast cancer. Now when I rotate the 3D graph, we check whether the class overlapping is there or not. This is the 2D. When I rotate it, no, okay. So this is the portion. If the minority instances are here, then they may get overlapped by this majority class instance. But that is not the case here. You just check this video. Hello? Haji? Haji. Okay. So, okay. Okay, sir. Okay. कोई बात नहीं. समझिए. हाँ. ओके सर. 100% चलो. हाँ एसएम सर. ओके हाँ. હું તને ફોન કરું સર 5 મિનિટ રહીને મારી લેક્ચર ચાલુ છે. હા. ઓકે. એ હા. શ્યોર સર શ્યોર. તમે કહેવાનું જ ના. ઓકે સર. હા. Okay. So this is for the next data set, that is the HM. Now so that is 2D graph. When I rotate this cube, we can see that is the overlapping. Somewhat overlapping is there. Okay, somewhat overlapping. Now let me stop here. This is the negative class instances. This is the positive class instances. If you rotate this 3D into 2D form, then some of these instances are overlapped by the positive instances. See here. Okay. Now I hope that now you have a clear visualization of the class overlapping. By just looking into 2D graph, we are not sure whether the class overlapping is there or not. But by visualizing in 3D, we can sure, yes, we can. There is a class overlapping. Now this is for subtle data set. So this one, the small dot is represent all the 49 negative instances, and this line represent positive class instances. So when I rotate this into 2D form, we can see here that large amount of negative instances are overlapped by the positive instances. Let me do this. Okay. Now this is mammography. Now look at here. This is the 2D. Is equivalent to the MDS plot. We are going to see that. So this is the 2D image. Now see the amount of overlapping here. This is the 2D graph. Let me rotate it. See the overlapping. All these negative class instances are overlapped by this dense area of positive class instances. Now let me give you here the properties of the mammography dataset. Mammography dataset has 260 negative class instances, 216, and around 10,000 positive class instances. So all 10,000 positive class instances are here. and that 200 negative class instances are here. Now, if I rotate this and make it 2D, I can see that major portion of negative class instances are overlapped. Now, overlap, that means what? That means there is a high similarity between the positive and negative class instances, and that means the SVM has worse performance for mammography data set. Now, see this, first of all. I hope that my video is visible. Let me know if the things are not visible to you. Huh? Okay. Okay. So next move to the now here. Okay. So this is the 3D. So we are here. So okay, we see we just saw that 3D in 3D there is no much class overlapping for the cancer data set. Okay. This is for new thyroid data set. Again, this is the 3D image. If you remember, new thyroid data set has 3 classes. This is the first class, this is the second class, and this is the third class. Okay, and this is the majority class as well. So this is the 2D graph with 3 colors of dots. So yellow, purple, and then light purple. So here there may be some sort of overlapping that we can see here. This person. Okay, this person. This is for HIV data set. So this 3D image, just we saw this in that video. When we rotate, we have this 2D image. So there are some negative instances on the boundary line, and okay, but still we are able to see some of the yellow dot in between the purple dot. That means the overlapping in case of HIV is less, because we can see here, we can visualize at least the dot in between the purple point. But in case of mammography, here, look at here. There is a minority, there is a negative class instances here, but it is completely covered by the positive class instances. Here we are not able to see much yellow dots. And even here we are not able to see any yellow dot. So that means in mammography we have a large class overlapping. Now the question may arise that how to create this 2D and 3D graph. So let me show it. First of all, let me close this R Studio. I hope that okay. So this is the tool that I use for the 2D and 3D graph. So that's the Bluewish tool. So first of all, let me import the data set. I'm going to create the visualization of 2D and 3D graph for the given data set. Okay. And before that, I already converted the multi-dimensional data into the 2-dimensional form using MDS. So I hope the steps are clear. So let me select this. Let me close this window as well. Okay. So first of all, let's see how the 2D graph can be plotted. Okay, so this is the mammography data set. Okay, let's get color coding for the different class. So by this you can select the colors for the class. Okay, the attribute we have to select. We have to select the class attribute. Now we can distinguish using the color coding. Okay, now see this. So these are the highlighted minority or negative class instances. This is the graph. Okay, so this way you can plot it 2D graph. So here we are not able to see, right? So now data that you have to identify. Now I want to make sure there is a overlapping. So for that, I will plot the 3D graph now, 3D scatter, so that I'm sure that yes, there is a overlapping. Okay, so this is the 3D graph. Let me rotate it. Now see, when I rotate it, you will see the complete overlapping, right? Okay. You can rotate. Okay, see here, complete overlapping you have. You can visualize this overlapping, right? In this case, this is one class instances. Say for example, negative class instances, and this is the another class. Okay, on z-axis we have a class. So this is the another class, positive class, and this is the negative class. When I rotate it, I can see here the overlapping. Okay, even I can do this. Okay, so that way we can create the 2D and 3D using GlueVis tool. So let me close this window now. Okay, so we are here. So okay, so this is for the last one, for the subtle. So in subtle data set, here, if you note here there is a dot, some dot. You can visualize some dots. Okay, so out of 49, obviously subtle data set has a largest imbalance ratio. That means the negative class instances are very few. But even if the few instances are visible here, that means there is a less class overlapping in case of subtle data set. Okay, now with this observation, we move further. So that is what the observation from the class overlapping. And the next one is one more thing that I want to show you, that I want to highlight, is you have to also check whether your class is surrounded by the majority class instances or your negative class instances are surrounded by the positive class instances. Here you can see this is the Mulligan, is the negative class instances. This is the instance which is surrounded by the positive class instances. Now, if you apply KNN algorithm here, then KNN algorithm is going to misclassify this instance. Why? Because in case of KNN, let's take the value of KNN, K is equal to 5. So it will check the class label of the instances which are nearest to this instance, 1, 2, 3, 4, and 5. And all these 5 instances has a label that is menu. So it will misclassify this instance as well as menu. But this is actually Mulligan instance. Okay, so if your class object are scattered and surrounded by some other class objects, then there is a high chance of misclassification. Now, after all these things, what our finding is, what are I want to say my observations. If there is an exclusive relationship between the target variable and independent variable, then decision tree can perform better. That we can identify from that multivariate attribute distributions. So as per the multivariate attribute distribution, the cancer data set has good relationship between the dependent and independent variable, and subtle data set has good relationship, shows good relationship. Second thing is, if data and class overlapping is present, then support vector machine would not perform optimally. Third observation, if there is no exclusive pattern between the dependent and independent variable, okay, there is no exclusive pattern. However, data is separable, then SVM perform better. That means for some data set, we do not able to find the good relationship between the dependent and independent variable. But still the data or the class is, there is a less class overlapping and the data is linearly separable. So at that time, SVM perform better as compared to decision tree family. In HIV data set, class overlapping is less. If you remember, we can see here the yellow point in between the purple point. So the yellow point are not completely hidden under the purple point, like in the case of here, in the case of mammography. So that's why in HIV data set, the class overlapping is less. And attribute distribution do not show much minority dominant distribution bar. So that means the SVM is going to perform well in case of HIV data set. But that's okay. In machine learning algorithm, as per the theory of the no free lunch, we cannot say that particular algorithm, particular XYZ algorithm is going to perform well in each and every case. No, we are not sure. Even if the neural networks, even in the case of neural network, we are not sure that the neural network is going to perform well for each and every data set. And that's why the study of data is important. To identify the most ideal algorithm for our data, it is important to understand the quality of the data. And to understand the quality of data, you have to perform this study. Now, this is the performance of algorithm. 3 algorithms I use: CART, J48, and SVM. So 2 are the decision tree based family. The CART algorithm use the Gini index. J48 use the information gain. So see here, as I told you that mammography data set has highest class overlapping, and that's why the SVM, this bar is for SVM. The SVM has less performance. While in the case of cancer data set, we see that cancer data set is very good data set. It has very good multivariate attribute distribution. There is no class overlapping. Even small disjunctions are absent. So that's why the performance of all the algorithms, all 3 algorithms, is around 0.9. Okay, the prediction rate is around 0.9. The lowest is for CART algorithm, but it shows in and around 0.9% of accuracy. Now, surprisingly, subtle data set has highest imbalance ratio, but still we are getting very good performance for the decision tree. Why? Because there is a very good attribute, multivariate attribute distribution bar for the subtle. And that's why it is possible for the decision tree algorithm to use that attribute as a splitting criteria. And if they use those attributes as a splitting criteria, they will get very good performance, around 1. That means 100% accuracy for the minority or negative class instances. And we observe some sort of overlapping during the class overlapping graph, from the class overlapping graph. So that's why SVM has little less performance as compared to decision tree. Even in case of diabetes, there is no good distribution, there is presence of the small disjunction, class overlapping is there. So we have a moderate performance for all three classifiers. So that means whatever we discuss, we found on the data characteristics. We can see here the effect of those characteristics in the performance of. So that's why to decide the performance of classifier, the data difficulty is important. Now let's So this is the finding. We got the base result for the breast cancer data set followed by subtle and new thyroid data set. And if you see the data difficulty levels, you will have a similar order. You have a very less data difficulty in cancer data set followed by subtle and new thyroid. For cancer data set, the algorithm have 0.95, 95% of accuracy. For subtle, it is 91% of accuracy on average. For new thyroid, it is 82% of accuracy. For HIV data set, we have a accuracy in the range of 82, around 82, 70 to 80. And we have a very less for mammography because we know that. Now let's see again the distribution, why we getting less accuracy for mammography. Let's recall that thing. This is the first thing, that is multivariate attribute distributions. Okay, this is the first thing, that is multivariate distribution. From multivariate for mammography, in multivariate attribute distribution, we are not able to find the red colors. That is red color bar, which is dominated, which have a dominance. So that is for failure for the mammography. Then in case of small disjunction, this is D is for mammography. Again, we have a very worst disjunction in case of mammography. Second drawback. Then class overlapping. This is the class overlapping. There is a worst class overlapping in case of mammography. So that means we have a very least accuracy in case of mammography data set. So the missing value and noise is not the every data is not the all the data difficulty that you have to address. There are some other data difficulties that you need to consider, and that's what I explained in this session. Now let's find out reasons. In case of cancer, we observe least class overlapping. We observe 4 minority class dominated clusters. Multivariate attribute distribution is good. So almost all factors favors the machine learning algorithm. So that's why machine learning algorithm perform well. Subtle data set. Subtle has largest imbalance ratio. So that is a difficult point. It has largest imbalance ratio. That is the one of the difficulty. But the other characteristic, the data quality favors the classifier because the class overlapping is less. Subcluster analysis, we found that there is no disjunctions. Okay, so that's why even if the data set has largest imbalance ratio, still we are getting very good accuracy. For HIV data set, class overlapping is greater as compared to the cancer and subtle, but still it is less as compared to the mammography and diabetes. There is no minority disjunction, and the multivariate attribute distribution shows minority dominated attributes, and that's why J48 and CART algorithm, which are decision tree algorithm, shows good result. However, due to moderate class overlapping, the SVM performs suboptimally. Mammography, I already explained that thing, why we are getting very less. Okay, so I hope now the data difficulties is clear to you. So next we are going to analyze, we are going to do the evaluation of evaluation parameters. I hope that up to this, it makes sense to you and you found this important. Okay, so next thing is, now in this session, I want to highlight some of the important points that we need to consider. As a machine learning expert, you should be aware about these things, because just understanding of machine learning algorithm like decision tree, neural network, SVM, and CART is not the sufficient. The thing that you need to understand the data set as well, because that data set has a large impact on the performance of the machine learning algorithm. So sometimes we try to tune the machine learning algorithm, but we are unaware that the data has difficulties. You have to solve those difficulties. Then it will automatically increase the performance of algorithm. Now, after this, I'm sure that now tell me, if one machine learning algorithm, if I am using the neural network and I'm getting the 90% of accuracy, do I implement that neural network into the production server? Do you think that I should implement the machine learning neural network algorithm just because it shows the 90% of accuracy? I should implement into the production server without looking into some other parameters? The answer is no. I should not do that. By just seeing on the very high accuracy of any algorithm, we should not come to the conclusion that yes, our algorithm is best. Yes, we can do this for the tasks which are not critical. Like if we are building a machine learning application for some social media, some text, some sentiment analysis kind of work, then it's okay. There is no need to look into some of the critical point, because even if you misclassify the sentiment, then it's okay. There is no harm into that. But suppose you are building a machine learning algorithm for prediction of the for diagnosis of the COVID patient, and you misclassify that, then misclassification cost of that misclassification is used, because that patient think that he is COVID free, he is going to spread the disease in the society, and that will create a large problem for the administration. Even it may be possible that he might lose the life. So that's why for some critical application, the evaluation should be holistic. So I want to highlight one disadvantage of the evaluation of performance measures. So what is that disadvantage? Let's see. Now here I take one synthetic data set with two class, positive and negative. So original data distribution is I have 100 instances. Out of that 100 instances, I have 70 instances belongs to positive class and 30 instances belong to negative class. So this is the original data set. After the classification, I implement one algorithm. So algorithm gives me the confusion matrix, and that confusion matrix is the true positives instances are 60, true negative instances are 10, false positive are 20, and false negative are 10. True positive, that means the positive instances which are truly predicted as positive. So out of total 70 positive instances, it truly predicts the 60 instances. And the algorithm misclassify 10 instances. That's why the false negative is 10. Out of 30 negative instances, the algorithm correctly classified 10 instances as a negative instances. So the TN is 10. So that means the remaining 20 are misclassified as a positive, but they are false positive. So that's why the false positive is 20. So we have this confusion matrix. Now let's calculate the performance measure, some of the performance measure. First one is accuracy. 0.70, very good accuracy, pass. Recall, 0.85, very good, pass. Precision, 0.75, pass. F measure, 0.79, pass. Okay, so by just looking into the four measure, we come to the conclusion that our algorithm is very good, because it's showing the all the parameters in and around 0.7 70%. This means 0.70. So that means our algorithm perform well. But what about Gmin? That is 0.53. Okay, that's okay. That is also good, 0.53. But by looking into these parameters, you miss this one. That is 0.33%. So your one class that has a less representation in data set is completely overlooked by your machine learning algorithm. And just imagine that if you are building, if you are developing machine learning algorithm for nuclear plant, and this negative instances is very important, then in that case, this algorithm is not applicable for such a critical application. So what is the problem then? The problem is with these performance measures, because these performance measures are called a biased measure. They are biased towards the majority class. So all accuracy, precision, recall values are biased toward the positive class, which cover the major part of data set. F measure is also biased toward the positive class. Gmin value is somewhat higher than the true accuracy of negative class, but comparatively shows good result, good balanced result. But still it's showing 0.53. So that is the drawback of evaluation matrix.
Sir, excuse me, sir.
Yes.
Sir, are you showing something on the slides, sir?
Yes.
Sir, we are presently viewing only mammography slide is visible, sir.
No, it is visible. Evaluation slide. Evaluation slide is visible.
Evaluation slide, sir.
Evaluation of
Yes, sir.
measures.
Evaluation is visible.
Okay, sir. Okay. Okay. I'll check with my internet connection.
Yeah,
Sorry,
yeah.
sorry for
Please
interrupting, sir.
check. Yeah, please check. Okay. So that is the problem we need to address. Now let me explain this thing with the practical example. I use one phishing data set and I implement one algorithm. Okay. Even ROC graph. Let's talk about the ROC, because everyone says that ROC is the very good performance measure, but it is biased too. So what is ROC? That is the receiver operating characteristic curve. By plotting the ROC, after the plotting the ROC, what you have to do, that plot is true positive rates versus false positive rate. Okay, so you have to calculate true positive rate and false positive rate, and you have to plot the graph, and then you have to measure the area under the curve. So that is the ROC. So, but ROC is even biased towards the positive class instance. Okay, so let's analyze this thing, this result. So after the implementation of machine learning algorithm for detection of the phishing, this is the confusion matrix that I got. So total around 23,000 phishing instances are there. Phishing URLs are there. When I use the machine learning algorithm, I'm able to detect almost all the phishing URLs. But I completely misclassify all the legitimate URLs. That means, okay, now after this confusion matrix, these are the parameters. What is the TP rate?
Sir, your
0.9.
confusion matrix is not visible.
So reshare the slides, sir. Reshare it.
Okay, okay.
Reset the
Actually,
slide
my
so-
screen is all okay. Let me reset this thing. Now I hope it is visible. Is it visible now?
Yes, sir.
Okay, thank you.
ROC is visible.
Okay, thank you. Yeah. So this is the confusion matrix that I'm getting. Okay. So I'm talking about this. These 2000 legitimate instances are misclassified, all 2000 instances. But still, from this confusion matrix, when I calculate the TP rate, precision, and F measure, what I'm getting? 0.92, 0.84, 0.882. So that means I am getting everything good. But the problem is, this algorithm is going to block everything. It just not block the phishing URLs, but it is going to block the legitimate URL as well. Even if you are getting a very good accuracy and very good precision, recall, and F measure, and everything, but you are going to block everything. Now, if you block everything, that is not the solution. So the evaluation parameter should be capable to highlight this kind of result. So we just 1 year back, we proposed 2 evaluation parameter for this kind of difficulty, that is called IRW mean and B mean. So this is called imbalance ratio weighted mean and balance mean. So when I calculate the value of IRW mean and balance mean for this result, for this phishing result, what I am getting? 0.016. Balance mean 0.46. Now this highlight the thing that we have a very bad result for some class which is important to identify. In this parameter, this IR value define the importance of the class. If you think that negative class is important, then you need to tune this IR value, and by tuning this IR value, you can evaluate the result of machine learning algorithm where it will give more importance to the negative class. Okay, so this way we try to minimize these adverse effects. And the last one is, okay, we had seen some of the difficulties. We also identify that how to visualize those things. Then we also discuss about the evaluation. Now last one is we discuss one of the difficulty, that is called data unbalance, and the remedies to handle that data unbalance is there are 3 techniques. One is use the data level sampling. What data level sampling will do? It will just balance your unbalanced data. It will just balance the unbalanced data. So in unbalanced data, for example, in unbalanced data, we have a 1000 positive class instances and only 10 negative class instances. By applying this data balancing technique, if you apply oversampling, then it will create the result like 1000 positive class instances, 1000 negative class instances. If you apply the undersampling, then it will do like this. It will create 10 positive class instances and 10 negative class instances. So here, in case of oversampling, it will generate the new minority class instances. That's why it will convert the 10 into 1000. In case of undersampling, it will reduce the positive class instances to 10. So in both the case, it will try to balance the data. Some of the techniques which are used for oversampling and undersampling, well-known algorithms are SMART, CURT, SCURT. SMART has more than 3000 citations till date. So you can understand the importance of the SMART algorithm. More than 3000, 3500, I think, citations are there for the SMART algorithm. CURT is used for undersampling. SMART is used for oversampling. And SCURT is the special which combine this technique. That is it, SCURT. Okay. So that is I think, out of the scope of this session. Second option is use algorithmic technique, where you have to modify your algorithm. you can use the cost sensitive algorithm using the feature selection and feature weighting. Third technique is one versus one and one versus all technique. Then one versus all, one, that means you have for two class build two classifier model and then combine the result. One versus all is used for multi-class data set. So these are some of the remedies to handle the unbalanced data difficulties. And then that's it from my side. Thank you very much for patiently listening me. And I wish you all the best for happy data learning with machine learning. But don't forget to learn the data before applying the machine learning. And I also like to thank team FTP, Computer Engineering Department of Government Polytechnic Gandhinagar. And that's it from my side. Ghanshyam sir, over to you.
Okay, thank you very much, sir, for such a knowledge-rich session, and this was really wonderful. So, dear participants, we are having few more minutes. If you want to ask any questions, then please grab the opportunity.
Hello, sir.
Yes.
Mahesh here. Sir, can you just quickly put things in a hierarchy? Means, let us say, if the first time we get a data set, then which is the first step? Whether we should go for means first we should remove NaN value and then we should prepare for this function, and also can you just put in steps that
Yeah.
this thing that this should be done?
Yes. Now, whenever you have a data set which you try to find out the numbers of dimensions that the data set has. Okay. Then try to find the size in terms of number of instances that you have. Then analyze whether it is a supervised or unsupervised. That means is it a pre-labeled data? Yes. Yes. Okay. So that is the first thing that you have to identify. Then you have to check whether you can remove some attribute. Now, why I'm telling this? Suppose you have a 1000 attributes in your data set, but some of the attributes are redundant. Some of the attributes are related to each other. So at that point, you have to remove those related attributes, that duplicate attributes. So that is the second step. So in that way, you can reduce the dimension, because if you go with the 1000 dimension, or let's say, for example, 100 dimension, then your machine learning algorithm will take more time. That is the first drawback. Second drawback, the machine learning may get biased because of towards that redundant attributes. That is the second drawback. So you have to find those related attribute, duplicate attribute, and all that things. Okay, that's done. Then what you have to do now, you have a very good data set. So try to find out whether there is a noise, whether is there any missing value. Handle that missing value, fill the missing value with the main value, handle the noise with the main value. That's it, you done. Now, next thing that you have to do is now start the analysis of the data. Do the multivariate attribute distributions. Check the class overlapping is there or not. Okay. Then after that, once you have everything in front of you about the data characteristics and all that thing, now you are ready with the machine learning algorithm. With the machine learning algorithm, you can select the best machine learning algorithm for your data set. So that is what I think what you should follow. That's obviously generalized steps. Okay. Any other question?
Okay, sir, I think you covered all the fundamentals, so they may not have any questions for that. Thank you very much, sir, once again for such a beautiful session.
Thank you very much, sir. Thank you very much, Computer Department and Team FTP. Thank you, sir. Thanks a lot.
Right. Thank you. So, dear participants, we are ending first session of the day here. We will start our second section right at 12:30 p.m. Please join few minutes before. Thank you, all of you.
Okay. Thank you very much. Thank you very much.